Daniel.
Yeah. So, I mean, in some sense, you can view this talk as an answer to Leonid's question in the last talk. But basically, this is a combination of part of a paper that's already on the archive from last fall on fault tolerance in small experiments. But a lot of it is part of a bigger project that's still in progress. So you'll see some of the rough edges at various points. So let me start by just making the distinction between error correction and fault tolerance. So error correction, this is the overarching theme of the conference, obviously, is you have some number of qubits, say, that are encoded using extra qubits in a quantum error correcting code. But the distinction, the key distinction with fault tolerance is that error correction assumes that your gates are perfect, whereas fault tolerance does not. And associated with that, error correction, you're trying to store some information unchanged. Whereas fault tolerance, generally you want to do operations on information that's encoded in the quantum error correcting code without losing the protection against errors. And so the upshot of this is that fault tolerance is quite a bit more complicated. And so you have to come up with kind of difficult constructions like we heard in the last talk. Whereas error correction, while not simple, is simpler. And so, for instance, one consequence of that is that quantum error correction has been demonstrated experimentally in a large number of systems. Whereas fault tolerance, well, in the past year, there have been 3 papers on the archive that are attempting to demonstrate fault tolerance. In my opinion, none of them achieves that, although they're getting fairly close. It may be that we'll hear at this conference about somebody who actually has achieved. But that's a current thing, whereas these experiments go back a number of years. Okay, so I realized when making this talk that I was probably going to say various things using some terminology that might not be familiar with everyone. So I thought I'd start out with the glossary. So one of them, I should say that basically everything I'm going to talk about is going to be in the circuit model. And that turned out to be a big enough and complicated enough project by itself. But it's definitely an interesting question to try to extend this beyond the circuit model. And so one term I'm going to be using is a circuit element. And by circuit element, I mean kind of the fundamental unit of a circuit. So obviously when we talk about circuits, we usually think about quantum gates as a fundamental element. But that's just one type of circuit element. You also have state preparations right at the beginning of the circuit, or sometimes in the middle of the circuit. You want to prepare, say, a qubit in the state 0, or multiple qubits usually, to use as the input. And so that operation can have errors as well. So we should include that as a separate part of the circuit. And similarly, measurements can have errors, so we should include those. And circuit element is just kind of my name for any of those things. Physical qubits, of course, the individual qubits that are making up your quantum error correcting code, whereas the logical qubit is the state that's encoded in the quantum error correcting code. And I'll probably be saying qubits, but it doesn't really have to be qubits. Qubits, any dimension, works just the same in most cases. So gadget, that's a terminology that's more specific to fault tolerance. So a lot of fault tolerant protocols work by, you take each circuit element and you come up with some more complicated circuitry that implements that circuit element on encoded states. So for instance, you might have a gadget that creates a logical 0 state, right? And does whatever checking you need to do to verify that and make it fault tolerant. Or you might have a gadget that implements the controlled NOT gate on the logical qubits. And so the gadget is usually a component of a fault tolerant protocol. I actually don't know of any protocol that's not built up out of gadgets, but I don't think, but there's no kind of intrinsic reason that you have to have gadgets, as far as I can see. So code block. So frequently, the way these the fault-tolerant protocols work is you'll encode 1 qubit in n qubits And so if your circuit, of course, has many logical qubits, you're going to encode each of them separately using n separate qubits. Again, you don't have to do it that way. You can encode many qubits in n qubits all at once. But quantum error-correcting codes, they tend to have some sort of natural size. That's how the code is defined. And that's called the code block. And most of the time, your computer, fault-tolerant computer, will be made up of many different code blocks. Some of these terminology I guess may just appear once, and then I'm never going to use them again. But I thought I should get them out of the way. So a physical error is an error that's occurring on physical qubits. And generally, I'm going to talk about single qubit physical errors, but you don't have to. And then logical error, of course, is an error that occurs on logical qubit, which is usually what you want to try to avoid. And then there's another subtle distinction here. So the errors are errors that are on the state. So you have the state at some given time, and you can compare what it's supposed to be with what it actually is. And if they're not the same, that means there's been an error. Now, a fault, on the other hand, is a term that I'll use for a gate or other circuit element, physical circuit element, that's not operating correctly. Okay? And so the distinction is not necessarily huge, but sometimes it's crucial. And then the error rate of a circuit, that's a term I'll definitely be using a lot. And in this case, what I want to use that for is we'll run the whole circuit. We'll get some classical, we'll do some measurements at the end. We'll get some classical probability distribution. And you can compare that to the output of the ideal circuit if there were no errors. Okay? And depending on exactly what you want to measure, then you can look at the probability that there's an error there. And that's the error rate of the circuit. Or if you're looking at an output distribution, you could look at, say, the statistical distance between those classical output classical probability distributions. Okay. So, what is fault tolerance, right? That's the goal of this talk, to answer this question, what is fault tolerance? So if you ask most people what fault tolerance is, they'll say, I have no idea what you're talking about. Why are you asking questions to strangers on the streets? So go bother somebody else. But if you ask somebody who actually kind of knows what fault tolerance is, and in particular quantum fault tolerance, you'll probably get an answer a lot like this, as you saw just a few minutes ago when Leonid asked Ted what he means by fault tolerance. So something like this, which says a fault-tolerant protocol is one for which a single fault in the circuit, remember that's a single, say, gate going wrong, can only produce one error per block of the code. Okay? So the idea here is that errors cannot spread too badly, right? One thing goes wrong. That doesn't happen very often, but when it does happen, we only want it to cause one qubit to go wrong. That's actually a little too strong, because whenever you have a 2-qubit gate, if that gate fails, there's always a possibility it can cause 2 errors. Or if you get a failure right before the gate, the error can propagate to 2 different qubits. But the whole idea of transversality is that we can ensure that those 2 qubits that are wrong are in different code blocks, and so they can be corrected separately. Now, the problem with this definition, I mean, it can be made more precise. This is a little bit hand-wavy, and actually everything I'm going to say is going to be at least a little bit hand-wavy. But the problem with this is that, well, there's actually a lot of problems with it. So, okay, so the first problem is it's not actually a necessary condition. So there's protocols, for instance, all the way dating back to the early days of fault tolerance. So Haranov and Ben-Or came up with protocols that had what they called spread 2, okay, or more. And what that means is that one fault could cause 2 errors in a code block. And of course, that's less good because you have to correct both of those errors. But if your code can correct more than 1 error per block, it can be acceptable. Right? And it will still kind of cause some improvement. So this is not a good definition if you want to encompass all existing fault-tolerant protocols. And in fact, a lot of well, I wouldn't go so far as to say a lot, but some of the more recent ones, and including the protocols we just heard about from Ted, at least bend this rule in this way, if not break it altogether. But another problem with it is that it's also not a sufficient definition. So for instance, if you want to talk about phase error correcting codes and fault tolerant protocols for those, or bias noise, or a variety of things like that, this is not going to help you, right? Because it maybe captures part of what's going on, but if you have one fault that causes an error of a type that you don't know how to correct, even though it's just a 1-qubit error, this definition is clearly not leading you in the right direction, right? You need to add something to it in order for it to be right. Another problem, like I said, we're kind of on the verge of getting experiments that actually demonstrate fault tolerance. And this definition is just no help at all for evaluating those experiments. All it can tell you at best is that, oh yes, this is an experiment that implemented a fault-tolerant circuit. But it tells you nothing about whether the errors were low enough to actually see any improvement in any kind of meaningful way, right? It's not interesting to implement a fault-tolerant circuit with error rates, of 10% because the error correction is not helping you. It's actually just hurting you. And then finally, and this is more subtle, but I think also kind of important, is that this definition kind of has a lot of model dependence built into it. It's kind of assuming that the protocol is broken up into gadgets, which, as I say, doesn't seem to be necessary to me. And it's making some assumptions about the nature of the error model, which I'd like to avoid in order to have protocols, for instance, that deal with bias noise or other kinds of weird error models. Okay, so that's getting into the question of why actually we need a real definition of fault tolerance. And maybe I don't need to motivate that, but I think it's a good idea to understand kind of the different ways this could be applied. So one of them is just that we kind of have seen in recent years an explosion of new ideas for fault-tolerant protocols and fault-tolerant gadgets. And it really would be nice to know exactly what it means when you come up with a new gadget, right, Leonid? How do you know it's fault-tolerant? What does it mean for it to be fault-tolerant? And so we'd like to have a definition which kind of encompasses all the possibilities. And if you come up with an idea for a gadget, you can check it against that definition. And moreover, maybe this definition, by opening our horizons a little bit, can help show us the way to come up with new protocols that we might not have thought of otherwise, and might be better than existing ones. So let's see. So this one I mentioned a couple of times. If you want to come up with fault-tolerant protocols for bias noise or for some other kind of non-depolarizing channels, that's I think, an important thing to do. It's a big open question. It's very difficult to do. But it's going to be impossible if you don't have some criterion what it means to be successful. And so another one, we heard, for instance, this morning about how the states of a holographic system can be described in terms of a quantum error correcting code. And so it's an interesting question, I think, to ask if fault tolerance can be applicable there. I mean, if the states are quantum error correcting codes, then maybe it makes sense to say that the dynamics of a holographic system should be fault tolerant operations in some sense. But what does it mean in some sense? Well, we have to know what fault tolerance means in this context. The error model is a bit different from what we normally deal with, and the whole framework is a bit different. And so we need a definition of fault tolerance if we want to talk about these things that applies in that situation. So then there's this issue of experiments, right? What experimentalists are doing these experiments, how can we say if they succeeded or not? And how can they say if they succeeded or not? And then finally, for me, this is actually, like I said, part of some bigger project, which is to put the whole theory of fault tolerance on a more systematic and rigorous basis. And so I'm not just interested in defining fault tolerance. I actually want to prove stuff about fault tolerance. I want to prove, for instance, thresholds in protocols where we haven't yet proven a threshold, where maybe we have simulations that suggest very strongly that there's a threshold. But it would be nice to have a rigorous proof to get some lower bound on the actual numerical values, for instance. Or extend existing simulations to error models where we haven't been able to simulate it yet. And also, you could potentially use these ideas to prove more general properties of fault tolerance, like upper bounds. Okay, so what's a fault-tolerant protocol? Well, all of the fault-tolerant protocols will have the same structure, which is basically that there's some map from ideal circuits to circuits, encoded circuits, which are supposed to be fault-tolerant. Okay? That's fundamentally what a fault-tolerant protocol is. And we want to say that these two circuits are kind of the same, right? This is an encoded version of this because there should be some decoding map where when you make a measurement at the end of the circuit, you get some classical distribution, and then you can decode it into an output distribution that's the same, or at least very close to the output distribution of the original circuit C. Okay? Sometimes we'll be talking about finite size systems, in which case, well, we have to just assume the decoding map is not too complicated, because otherwise you could have a protocol where you say, well, let's forget about doing all this quantum stuff and just simulate it classically, and that's our decoding map. But if you are working in an asymptotic context, you can just say this decoding should be efficient, polynomial time. And one thing that's sometimes interesting to do is to draw the circuit C. Well, first of all, the circuit is not necessarily going to be an arbitrary circuit. Usually it's built up of some particular set of gates that you're using to make your fault tolerance. Usually that set of gates is universal, but it doesn't have to be universal. You can look at some smaller set, and all of these things will still make sense. And again, often the way these protocols are built is by taking each circuit element of C and replacing it with a gadget, but you don't have to do that. This is more general than that. Okay, but the unfortunate thing about what I've written so far is that none of it indicates anything about tolerance of errors, right? So we need to deal with that. So what do we want from a definition? Well, I mean, of course, it should apply to all existing fault-tolerant protocols, and also all protocols that we can think of, right? Everything that somehow satisfies our intuitive notions of what fault tolerance means. The other side is also important, right? We want it to exclude things that don't accomplish the goals of fault tolerance, right? So if you have something where errors, I mean, it kind of maybe looks a little bit like a fault-tolerant protocol, but it doesn't deal with errors, that's no good. So this one, for a lot of the applications that I said, you don't want to make any kind of assumptions about the error models. I mean, so the specific application of a fault-tolerant protocol might assume a lot about the error model. It might be a very specific error model. But the definition shouldn't make those assumptions, right? Because the definition only applies to certain error models, then it's not going to be useful in cases where you're dealing with some other error model. And it's also not useful for experiments where you don't necessarily know exactly what the error model is. You might have a good idea, but there's always going to be some elements of it that don't match your theoretical model. So again, a perfect definition should apply in the asymptotic limit, but it should also apply for finite size systems, because we are interested in fault tolerance in finite size systems. And there should be some way, if you have a theoretically presented protocol or an experimentally presented protocol, to verify that it's actually satisfying this definition. It might be difficult to do that, but that's a secondary issue. First of all, it should be doable, at least in principle. And finally, it should be not kind of arbitrary. It should not change very greatly what is a fault-tolerant protocol if you tweak the definition, tweak parameters in the definition. But unfortunately, I haven't actually been able to come up with any definition that satisfies all of these conditions. And it's a little bit frustrating, but I've kind of come to the conclusion that there isn't one. And that instead, the approach that we should take is to come up with a list of kind of fault-tolerant properties. And if you want to take a rigorous approach, you would say, OK, I have this protocol, and I can prove that it follows, that it satisfies these particular fault-tolerant properties. And then you have to pick the properties that are kind of most appropriate to the situation to use. OK, so let's get started on the actual definitions. So the first one, which is kind of maybe the closest to the one I showed before, So the one I showed before, remember, said that one fault causes at most one error. So one thing you could say is that a protocol is fault tolerant in the sense of improving the error scaling if the error rate goes from O of p to O of p squared. So this clearly is not going to apply to arbitrary error models. So this is the condition the main condition that's being violated here, is you need an error model where there's some error parameter p that you can adjust, and the error model makes sense of that regime. And then you can look at unencoded circuits. Generally, the output error rate of those circuits will be O of p. It'll scale with the size of the circuit as well, of course. But then when you encode it, if kind of the fault tolerance is working, the error rate should go down to O of p squared. Okay? And so, of course, the way you would verify this is by changing p. And so if it's a theoretical protocol, that's fine. If it's an experimental protocol, that's not so good. So that's the disadvantages of these protocols. Yeah? So the question is, experimentally, can you do the correction, not do the correction? No, but see, but that's not going to help you test. Sorry, let me repeat the question better. So experimentally, you can either do the correction or not do the correction. Well, first of all, that's not that straightforward. I mean, there's something like that, which I'll get to later. But you're doing all this extra fault-tolerant circuitry, and that has overhead. So it's not really fair to compare unless you're taking advantage of that. Yeah?
You can satisfy both of your cons very simply by comparing a first-order error correction with the second-order error correction. And then it becomes a very fair comparison. If you get zeroth order to first order, you compare first to second. And then all your cons go away.
Sorry, I'm not sure what you're comparing. You're comparing different protocols?
It's the same protocol. Go ahead. I'll talk to you later.
Okay, yeah.
John's just referring to family of nodes.
Yeah, that's what I thought. Okay, but look, none of that is actually answering this question, right? So to actually see that this definition is the case, you have to change the error rate, and you have to see how the final error rate would change as a function of the error rate. There's a longer discussion to be had here, I'm sure. But let me go through some of the other definitions, which are maybe closer to what some people are thinking about. Okay, now this definition does have nice positive aspects. So for one thing, most existing protocols, I think, do satisfy this definition. And of course, you can have versions of this where the error scaling is better, p cubed, p to the fourth. That's fine. And at least theoretically, there's a direct way to measure it. And clearly, if this is what's going on, then you can see that fault tolerance is working, right? It's doing something in the low error regime. But like I said, it has some cons as well. So okay, so the next definition is the threshold. And threshold is a pretty good definition. So what you would say is you'd say that the error model is below the fault-tolerant threshold for some circuit encoding. If for all unencoded circuits C, the error rate of the corresponding encoded circuit is below some constant epsilon. Okay? And this is a little bit arbitrary what this epsilon is, but at least in all the thresholds I know, this epsilon could be arbitrarily small. So the pros, obviously, a lot of times when we talk about fault tolerance, the goal is to get below the threshold for fault tolerance. And this really is the goal, right? If you can do this, then errors are totally under control. You can do, arbitrarily large circuits, and the errors never blow up. And moreover, it doesn't require you to know anything about the error model, right? This definition makes total sense. All you know is that there's some kind of multi-dimensional giant threshold surface, and the inside is the good part, and outside is the bad part, and this is telling you that you're inside. Okay? But But the big disadvantage in my mind is that this doesn't apply to finite size protocols, right? There's just, it doesn't even make sense, right? Because if you have only a finite family of circuits that you're looking at, well, there's always going to be some constant epsilon that they're all below, okay? And the idea of getting arbitrarily small error rate is also not meaningful for a finite size circuit. But the thing is that even for some infinite, scalable protocols, in the sense that they work in the asymptotic regime, it doesn't work for that either. So for instance, Shor's original fault-tolerant protocol required the physical error rate to be lower for bigger circuits. But it went down a lot slower than the size of the circuit. And so that was a big improvement over the state of the art at the time, which was no fault tolerance. So this is the sort of example of, he says, well, if I can achieve the threshold, then sure, we're definitely going to be happy with this protocol. But if I can't achieve the threshold, maybe it still makes sense to call it fault tolerant, right? So this is something that I would consider a sufficient condition, but maybe not a necessary one. Definitely not a necessary one. Okay, so moving on. So let's think a little bit more deeply about what we really want out of a fault-tolerant protocol. And what we really want is to be able to do some circuits that we couldn't do before with kind of limited error rate. And so let's codify that into a definition. So this is a definition. So we're going to say that a fault-tolerant, allowing larger circuits, is the circuit encoding is fault-tolerant if the set of unencoded circuits with an error that have an error rate less than epsilon is strictly smaller than the set of encoded circuits that have an error rate less than epsilon. Okay? And that's just saying that we're setting some target error rate that we're trying to achieve, and the fault-tolerant protocol lets us do more circuits with that error rate. Okay? And so that's a very attractive definition, right? Because it's saying exactly what we want from a fault-tolerant protocol, right? We want to be able to do more circuits. And it applies finite size, infinite size. Well, infinite size, not really, okay? Because for really big circuits, probably you're never going to get less than epsilon, right? Unless you're actually satisfying a threshold. So it's maybe not exactly what you want. And it is, however, something that you can directly test, right? You can imagine doing all the circuits in this family and see whether or not you're below this error rate epsilon. And it doesn't make assumptions about the error model. But the real problem with this one, from my point of view, is that this epsilon just has to appear out of thin air. You have to make up this epsilon, and there's no natural way that I can see to pick it. And moreover, if you pick epsilon wrong, you might get a different answer as to whether your protocol is fault-tolerant or not. Right? If you pick it, for instance, too small, then maybe your fault-tolerant circuits don't get that low, and then you're just out of luck. You'd say, no, it's no good. There's nothing that satisfies it either way. If you pick it too high, maybe everything satisfies it, or for everything of the size that you're considering, and that's no good either. And maybe even in between, there's some case where you're kind of not actually getting much improvement, and so you don't see the fault tolerance.
Doesn't it also lack some kind of structure on the bigger set S prime? Like I guess you could imagine that you get bigger sets, but they're kind of uninteresting sets of circuits or something, or there's some restricted sets?
Yeah, so the question is, maybe the bigger set S prime includes some extra circuits that you don't really care about. I think you can probably address by limiting the family of circuits that you're worried about. But yeah, there may be. I mean, I haven't examined this definition too closely, so there may be other problems with it that I haven't seen. I think I should say that for this infinite part, I suspect there's some kind of scaling version of this. I think probably you can make some sort of scaling version of this that does work in the asymptotic limit, but it still is going to have some problem like this, and then it won't work for the finite size limit. So you have to trade that off. Okay, so I'm going to end the list of definitions with the one that's my current favorite, and it has a number of problems too. So let me get that out of the way up front. But I think at least for the problem of how do you say if an experiment is fault tolerant, I think this is the best one. So I'm going to say that an experiment is, or a circuit encoding is fault tolerant, reducing error rates, if for every circuit C in the family that we're considering, the unencoded version of C has a higher error rate than the encoded version. Okay? So this is just saying that fault tolerance reduces error rates. Right? So that's sensible. That's kind of what we want to achieve, if not quite as directly as the last definition. It's good because it applies both to finite size and asymptotic systems, just in exactly the same way. It includes, the threshold includes the improved error scaling as special cases. And it's pretty similar to the last one, too, in some contexts. And it doesn't make an assumption about the error model. It can be directly measured, at least, again, in principle, of trying all the circuits in the family and seeing whether you get an improvement in error rate. But like I said, this is my favorite one, so I've thought about it a lot and talked about it a number of times. And so a number of defects have shown up in this thing. So sometimes, this is something that Ken pointed out, sometimes this definition is too strong. So for instance, if you have some subset of circuits for which the error rate is already quite low. So for instance, his example was if you have pure amplitude damping noise, and you have a circuit that just creates 0 and leaves it at 0, well, you won't see any errors. So the error rate would be 0. Right? And you're never going to get better than that using any kind of fault-tolerant circuit. Actually, it's going to be worse because you'll probably have some 1s in the circuit. So in that context, this definition would say you're not fault-tolerant when really you were just asking too much. Another example that Ken pointed out is that it can depend on some implementation details. So for instance, if you have, the 1 qubit error rate is quite low, the 2 qubit error rate is higher, then maybe your logical 1 qubit error rate is a bit higher, but your 2 qubit error rate is lower, right? So personally, I'm happy with saying that's not fault tolerant because some gates are getting worse. But it's also true that if you were to, just kind of mess up your experiment a little bit, so the 1 qubit error rate got worse, then you might satisfy this definition, right? And that's clearly cheating, but if you're not doing it deliberately, then you might not know that you were cheating, right? If you just weren't that careful with your 1 qubit error rates. And so that's kind of unappealing. But I think if you're kind of honest about it and really do try hard, it's reasonable to apply it in this case. And finally, and this is a problem that was pointed out by David Poulin. This is in my mind, a somewhat more serious problem for the general context, which is that this is you need to compare the error rates from the unencoded version with the encoded version, and that only makes sense if they're both kind of qubits or both in the same kind of system, right? So for instance, if you're doing an encoding of a qubit in an oscillator, then the physical qubit is a harmonic oscillator and will have one sort of error. And the logical qubit is an actual qubit and it will have a totally different sort of error. And it doesn't really make sense to compare the error rates between these systems. In fact, the circuits that you can implement on oscillators are going to be different in a formal sense from the ones you can implement on qubits. So like I said, this is not an ideal definition. It doesn't satisfy all my criteria. But it is good for a lot of purposes. And in particular, I think that if you want to do a fault-tolerant experiment, this is the definition you should be using. The previous one you could kind of do if you came up with some good epsilon about the number of circuits that you can do. But this one I would prefer. But there is still a lot of subtleties for how you actually would have to implement this experimentally. So first of all, for starters, we're probably not going to be having a universal family of circuits. So you need some other kind of limited family, and it could include both small and large circuits, and it could include circuits that are kind of regular and circuits that are kind of random, so that you're kind of exploring all the different ways the circuit can fail. Now, another thing that I've kind of not really talked about most of these definitions kind of, and the theoretical perspective, you could talk about incomplete circuits where you start with qubits and you end with qubits. But for an experimental context, you should always be talking about complete circuits where you create, you prepare your initial states using your experimental system. You do whatever gates you're going to do, and then you measure and get a classical output. And that's because we assume that all the quantum components can have errors. And if you leave some of that out, there's going to be some errors that are kind of missing from your examination, and it's not really going to make sense. And in particular, if you have non-Markovian errors, where you get correlations between errors in different parts of between faults in different parts of the circuit, then you're really in trouble if you don't do this. So in particular, I don't want to talk about error rates of individual gates. That's not something that's meaningful when you have non-Markovian errors. You should just talk about the error rate for the whole circuit. And then the last thing that's really important, and part of the reason of that previous con about like qubit in an oscillator, is you need to compare the encoded and unencoded error rates in the same system. So your logical qubits, you may have 2 logical qubits and 4 physical qubits, or 5 physical qubits. But you shouldn't measure the unencoded circuits in a separate 2-qubit system, right? Because that's a different system. It's going to have different error rates. You should do it in the same system, pick 2 qubits to use, and compare the error rate on that circuit to the one with the 5 qubits. Yeah, and so this means that you're not scaling different protocols to different sizes, anything like that. You're just fixing one particular code and size and looking at different circuits for that. And to actually do this experimentally, there's a lot of other complications. So for one thing, for small experiments, it's not so bad, but once you start to scale this up to larger systems with many logical qubits, what this error rate is the difference between the actual output distribution and the ideal output distribution. But to calculate that error rate, you need to know what the ideal output distribution is. And that, if you have many large qubits, that's going to be hard to do. Also, it requires a lot of statistics to actually get a good measurement because presumably the error rates are low. So that's a problem as well. And then finally, if you just really say, OK, I'm going to test every circuit in this family, that's an enormous number of circuits, right? It grows, well, more than exponentially with the size of the circuit. So really what you want to do is you want to test some subfamily that's representative somehow, and that convinces you and convinces other people that if you really had tested every circuit in the family, that you get the same answer. OK. So like I said, I've kind of gone through 5 definitions of fault tolerance. There was the first one that I didn't like too much, which is 1 fault causes 1 error per block. But then there's these 4 others, which I think are all pretty interesting and applicable in different situations. One is the improved error scaling. One is the threshold. One is that you can allow bigger circuits. And then the last one, that the error rates get reduced. Now, like I said, this is part of a bigger project for me. So here's a list of things that I would like to do, not necessarily as part of this project, but maybe sometime in the future. So one thing that is in progress is defining what it means to have a fault-tolerant gadget and to have a protocol that's built out of fault-tolerant gadgets. But to extend that from the existing definitions to more general protocols and error models. It'd be interesting to come up with fault-tolerant protocols that don't have gadgets. I don't know really if that's possible, but it's an interesting question. And like I said, prove properties that we haven't proven before about existing protocols. Then the more speculative things, come up with new protocols based on the new possibilities that are opened up. Prove some general properties about protocols. So for instance, Lucy Zhang and I had a paper where we conjectured that all fault-tolerant protocols were inherently topological in a particular sense. And so given an appropriate definition of what fault tolerance is, maybe one could try to prove something like that. And then finally is to apply fault tolerance outside the realm of quantum computing to things like holography. So thanks.
Thanks, Daniel. We have time for questions.